So here's the question that we have to ask ourselves. There's these question when we find an algorithm seems to be biased in some way, how are we supposed to measure that unfairness, right? And there's been kind of three classic answers to that question in the literature, three classic what we call observational measures. We're going to run through them really quickly. There are these three families. The first is just bare independence. The idea, this is sometimes known as demographic parity. The basic idea is that the attribute, like race, is statistically independent from the classifier, right? So that the basic motivation of this is that the treatment of the groups by the algorithm is equivalent, right? So however many resources the algorithm has to distribute, it's going to distribute them proportionally between the two groups, right? And it's going to fail if there's any association whatsoever between the attribute and the classifier, the risk score, even if there's also an association between the classifier and the target. Okay. That last clause there is what's motivated a lot of people to think about conditional measures, because they're worried about the goal of many algorithms is in fact to think about base rates or incorporate base rates. And so folks have thought about two different kinds of conditional versions: target conditional independence, where the idea is to equalize risks of misclassification between groups, false positive rates, or classification conditional independences like calibration or test fairness, where the idea is to equalize predictive value or informativeness of the classifications between groups, right? So basically a particular risk score gives you the same amount of information about the groups, the individual's risk of having the target variable, regardless of their group membership. Both of those are going to fail if the attribute is associated more strongly or more weakly with the target or the classifier than with the converse, okay? Because the basic idea is you're trying to see whether there's an association between, in this case, the attribute and the classifier, controlling for the attribute's association with the target. All right. That's really quick. So the basic idea is that you can't satisfy all these measures of fairness simultaneously. That's been the big result that's in the literature. And in particular, you can't satisfy it if there's a demographic disparity in the distribution of the target variable, the ground truth, and if the prediction is imperfect. Both of those are true in lots of different circumstances, right? And so these famous impossibility results have said, listen, we've got to choose one of these, right? The conventional wisdom is we have to choose at least one of these. And the real game is thinking about the normative implications of each of them, as Sina and Zach explored. Here's my slightly heretical view. I think these things were constructed they're constructed with enough causal and moral idealizations such that they don't really operate correctly in the actual unjust world. And in fact, we shouldn't aim to satisfy any of them given the injustice that we currently have and the causal associations that we currently have. So here's the question. What are the assumptions that underpin these classic observational measures? Like how are they actually idealized in various ways? Okay. So to start off with, I think the basic thing to remember about these observational measures is that they are motivated by considering what would be intuitively fair in the abstract, right? So the idea is, at least for instance, to think about demographic parity, the idea is, well, we want to make sure that there's no causal association between the attribute and the classifier. That seems intuitively to be the most fair outcome, right? or we want to make sure that there's a equality of distribution of resources between the two groups. That seems like proportionate to the size of the group, the relative size of the groups, right? That seems to be the most fair outcome in the abstract, right? And so they operate essentially with this kind of blind baseline. They think, listen, the best outcome is that A has no causal influence over C or T. And in fact, if this is true, if you have a causal structure like this, you're going to pass all of these tests, right? And the idea is, in the colorblind ideal, these algorithmic classifications are going to be completely independent of race, because race doesn't influence the outcomes, the target variable at all, right? So that's one, right? And the second thing that they kind of assume, or the second thing that they kind of assume, is that you should avoid disparate treatment. This is the big kind of the big wrong that motivates, I think, a lot of these cases. They think that the classic form of discrimination is one that involves disparate treatment, and that's one where the A is an explicit or implicit model feature, right? In the model, right? And so you get a kind of causal structure that looks like this, right? Where A is a cause of some, perhaps this is just the race, a race is an input variable, or perhaps it's some proxy that has been intentionally placed into the model in order to bias the classifier in some way, right? This is wrongful because A has a direct causal influence over the classifier, but not over the target variable, right? It's like a clear bias or distortion, right? And so race becomes associated with the risk score, but not actual health need because of some intervention that created the disparate treatment. And so the assumption here is that what this kind of gets cashed out in often is this assumption that it's unfair if a sensitive attribute causes the classifier but not the target variable, right? And indeed, if you have a classifier where the sensitive attribute causes the classifier but not the target variable, it's going to fail on all of these. Two, you should avoid creating disparate impact. So some disparities already exist, and the algorithm should simply avoid creating greater disparities, right? The idea being that the baseline is the kind of the perfect ideal situation where there is no disparity, but some disparities already exist, right? And the algorithm should simply avoid creating greater disparities. In this case, the claim is going to, so A in this case is going to be a cause of some model variable, for instance, is one way in which you can, of some model variable, and hence it's going to be associated with both T and C, right? So race, among other things, is a cause of zip code, which is a cause of low access to primary health care, which is therefore a cause of greater health need in the following year. And the kind of intuitive idea behind both these measures is that you shouldn't introduce, or in fact reduce, the association between the attribute and the classifier that does not already exist between the attribute and the target variable. Right? So here would be an example of impermissible disparate impact, right? A is going to, where A causes C, right? But the algorithm over or de-emphasizes A's causal influence over T, right? So A is associated with both C and T, but it's associated, it has a greater causal influence over C than it does over T, okay? And this is a kind of classic disparate impact case, right? Where the neutral algorithm widens existing racial disparities, not because it intended to do so, but because it used it used a set of features that weren't precisely calibrated towards identifying the target variable and instead added some extra discriminatory impact into the classification scheme. And indeed, in these kinds of situations, it's going to fail all three measures, right? But here would be a case of permissible disparate impact on these three measures, one where A causes C, but the algorithm simply reflects A's causal influence over T. In a sense, this graph here is going to end up being unfaithful, right? The data is going to perfectly balance the association between A and T, right? The basic idea is the classifier will perfectly capture race's influence on health need. And that indeed would be a defense to the legal claim of disparate impact, right? If the algorithm actually predicts health need and there's no other method of predicting health need that has less of an association with the attribute. Okay. So the idea is both conditional measures assume that capturing A's real influence on T is fair. And this gives you two second assumptions that I think are important. One is that if A is associated with T, it's going to be by virtue of it being fully mediated through the model, right? At least in a well-formed, accurate model. And then second, if A is associated with T, then it's fair for A to be similarly associated with C, right? It's fair for the model to capture that association between the attribute and the target variable in its classification scheme. All right. But my view is that these assumptions, A1, A2, and A3, don't hold in our actual unjust world, right? Or at least you don't have good reason to hold them. And that's for three reasons, right? The first is the historical oppression that we're dealing with, right? So remember, A3 claims if A is associated with T, then it's fair for A to be similarly associated with C, right? And that's the kind of underlying assumption behind both the conditional measures. But that just simply isn't true if you think about why A is associated with the target variable, which is because of historical injustice, not natural benign group differences, right? So race was a cause of wage discrimination, which is a cause of poverty, which is a cause of low prior access to healthcare, which is a cause of high health need. That's the causal chain that gives you an association between A and T. But the wage discrimination makes that causal chain illegitimate, right? So if that's true, perfect prediction of A's unjust association with T, while it will pass both conditional measures, isn't going to give you a fair outcome, right? And so we should reject A3 in the context of historical injustice. Similarly, this one's a little bit more complex. Unmodeled injustices are also something that we have to deal with right now. So it's not just that we have historical oppression and injustice that have influenced the association between A and T. Often we have ongoing explicit and implicit injustice or disparate treatment that's difficult to capture in individuals' input data, except as the sensitive attribute. So for instance, we know that there is racial bias in pain assessment and referral for diagnostic scan technologies using MRIs and CAT scans, etc. We know that there is a kind of implicit racial disparity there that's been shown in the data, right? It's very difficult to capture that causal chain it's very difficult to capture that association without simply referring to an individual's race. Similarly, we might think that workplace sexism actually does lower women's productivity in the workplace, and so there is an association between gender and actual productivity, the ground truth, right? but that association is very difficult to capture based on people's education and all the sorts of other variables that we might think are relevant, except by reference to their gender, right? And so what will happen is you'll get if you do a post hoc analysis here, is that you show that A influences T more than A influences C. So there's going to be less use of treatment by blacks controlling for the risk score. There's going to be lower productivity by women controlling for the prediction of how productive they were going to be if we weren't able to incorporate this in. And so this assumption that if A is associated with T, it's going to be fully mediated by the model isn't always true unless you're explicitly looking at sensitive attributes. And that's a problem, because it's going to mean that algorithms that try to capture A's influence over T, right, in order to satisfy these two conditions here, right, are going to simply compound the injustice, right? So if you have a model that doesn't capture this association here, right, it's going to fail both these measures, right? It's harder to see why it's going to fail the classification conditional measure until you sit down with directed acyclical graphs for a while and think about the open paths. But it will fail, right? And then if you try and rectify this, right, by trying to constrain the data set in some various ways, what that will require is that you lower black patients' health risk rating, right, or you lower women's predicted productivity in the classifier, right? But the only reason you're doing that is because you can't, is that you're simply modeling injustice into the classifier. Right?
Jon, you have around 2 minutes.
Okay, perfect. Yes, I'll be quick. So the final thing that's important, I think, is this idea that the first assumption that it's unfair if A causes the classifier, but not the target, the ground truth, is just simply false if we think that rectification of historical or existing injustices is permissible. So if we think that policies like affirmative action are permissible, but involve explicit disparate treatment, at least in some dimensions, right? Then they're going to violate all of these measures of fairness, right? But we might still think, nonetheless, that those policies are permissible, right? And so the idea is, if that's true, well, then A1 is false in a context of existing injustice where we might want to rectify that injustice. So in summary, you can think of this as a kind of like as a very down in the weeds version of Sina and Zach's talk. The idea that showing that there are specific ways in which these measures fail, given the assumptions, the idealizations that they make, and given the facts about the non-ideal world in which we actually live in, right, that make it the case that the application of those measures to the unjust world is likely to result in greater injustice, right, if we kind of optimize on those measures. All right. And you can read the full, I'll finish there, but you can read the full paper at my website.